Dense day today, as you could tell by the number of slides at the bottom left-hand corner. We have 102 slides to get through, so that is going to be fun stuff. Can you guys hear me and see my screen? Awesome, cool. So let's see. If we need to send out the slides in a bit, we can. So today is endocrinology and immunology. Unfortunately, these two topics are paired together for the TBR curriculum, but I'd honestly prefer if they were taught separately because I can go into an entire lecture on both of these individually. But good thing we don't need to be experts on immuno, and so we're just really going to try to familiarize ourselves with immunology. Endocrinology is a little bit more of the heavy hitter today, and so we will spend a significantly longer portion of time on endocrine, but because there are so many slides, I'm going to have to go a bit faster. So I'm going to try to keep everything on topic and as relevant as possible. But yeah, so let's see. Any questions before we get started and get going throughout our day? Endocrinology and immunology aren't really things that people have historically a super strong background in. So this is a lot of usually novel information, but hopefully we start to familiarize ourselves with it today. Alrighty, let's send out the slides. Alrighty, okay. So endocrinology, what do we need to know for endocrinology? So we're gonna look at the functions of the endocrine system. We're going to look at what hormones are, what the endocrine glands are, the different types of hormones, the mechanisms of actions of these guys, how they get transported throughout the blood supply, and their specificity. So they, even though they travel throughout the entire blood supply, a hormone only signals to its target tissues. So what are hormones? Hormones are messengers. So there's different types of messengers. So the endocrine system releases these hormones and they can control things like development, metabolism, growth, behavior. And so these guys are, as we talked about briefly in the last week, most often released from the HPO axis. And so they go from the hypothalamus into the pituitary gland and then into the bloodstream. And they travel throughout the bloodstream to messengers and messages to their target organs. The different classes of hormones, as we see here, are peptide, steroid, and amino acid derivative hormones. So the biggest thing I want you guys to know is the difference between peptide and steroid hormones. So peptide hormones are these long chains of amino acids that act as messengers. Because they're messengers, they are hormones. And steroids, typically derived from cholesterol, can act as messengers as well. And so you know some examples of them. The most common peptide hormone you'll see in different passages are things like insulin. So we'll talk about insulin in a bit, but insulin is a peptide hormone. And you might see things like cortisol, aldosterone, which we'll talk about later on as well. These are steroid hormones. The biggest thing you need to know what the difference between the two are their solubilities. And so the solubility really allows it, what gives it its properties, where are its receptors. And depending on the location of the receptors, can tell us more about its signal transduction mechanism. So we'll talk about that. What do I mean by that? Let's go over it. So the steroid versus peptide hormones, they differ in their binding sites. And it's because of their solubility. These peptide hormones are usually polar. And so polar things can't diffuse through a plasma membrane that has a nonpolar space. So because peptide hormones are polar, they will signal at the cell surface. So they'll have receptors at the cell surface. Steroid hormones, because they are nonpolar, they're lipophilic, they can diffuse through a plasma membrane. And so because they can diffuse through the plasma membrane, their receptors are often inside the cytosol. And so if you get a passage that tells you it's a peptide hormone or if it's a steroid hormone, you should automatically think, hey, where is it signaling? So the steroid hormones, as I said, mostly derived from cholesterol. And the biggest, trait about them is that, yes, they are nonpolar. They are lipophilic, and so that they can diffuse through the cell's plasma membrane, and their receptors exist in one of two locations, either free-floating with the cytosol or exist inside the nucleus itself. And we'll look at the signal transduction here in a bit. But yes, steroid hormones diffuse through the plasma membrane because they're lipophilic and signal receptors inside the cell. Peptide hormones are water-soluble. They are polar. They are lipophobic, so they cannot diffuse through the membrane, so they signal at the cell surface. And so because they have to signal at the cell surface, that's where their receptor is. You might get asked, hey, this polypeptide and your hormone exists. Where is the most likely location of its receptor? They may give you, cell surface, they might give you inside the nucleus, inside the cytosol, on the nuclear surface. And the most likely answer for that one will be cell surface for those. As you can see here, this is what I mean by steroid hormones diffuse in, and they can bind to a receptor inside the cytoplasm. So what are the three factors that really affect cellular response? So the first is the messenger concentration. So basically, if you have more messenger, you can activate more receptors. You can saturate all your receptors possible. So if you have more messenger, you can create a greater response because you've saturated all of the receptors, and saturating all of the receptors can create a larger downstream signal. So the first thing that affects cellular response is the messenger concentration. Second is the number of receptors. If you have more receptors, you can potentially bind more total receptors. So let's say we have 10 receptors all bound to their substrate versus 20 receptors all bound to their substrate, which is going to create a greater downstream signal, the 20 receptors. But what increasing the number of receptors also does is it increases the likelihood that the substrate will come into contact with its receptor. So as we see here, if we have twice the amount of receptors at lower concentrations, we still have greater numbers bound. And why do we have greater numbers bound? It's because we've increased the odds that that substrate will have found its receptor and can signal. So right off the bat, two factors that affect cellular response: number of receptor and messenger concentration. So what the body can do, and if it's getting chronically too high of signals, let's say you're chronically having this pathway that's signaling at high amounts, the body can actually downregulate the number of receptors. And what downregulating the number of receptors will do, it'll decrease the response. And let's say we have a really low response and the body wants more of it. And so what it'll do is it'll upregulate the number of receptors, let's say free floating throughout the cytosol or at the cellular membrane, depending on what the substrate is. So our body can upregulate and downregulate the amount of receptors to affect the response as needed. A few more people have joined, so I'm going to add the slides again. And then the last factor is the receptor affinity. So what affinity is, in just broad terms, is how strong or how likely a messenger is to bind to the receptor. So if we have a higher affinity, not only is that receptor going to be bound to the substrate tighter and longer, but it is also more likely to hold on to it at lower concentrations. So for affinity curves, I always like to draw lines. So if we want to bind 50% of our receptors, a receptor with a higher affinity for the messenger will require a lower concentration to meet that 50% than a receptor that has a low affinity for the messenger. You'll need a higher concentration of the messenger to bind that same 50%. So if a receptor holds on to a substrate tighter, it would thus have a higher affinity. And if it doesn't hold on to it as tightly, relative to a different one, it will have a lower affinity. So the three factors that can affect the response or the strength of response: concentration of the messenger, number of the receptors, and the affinity for the messenger. Just a question. So there's a question, do we need to know how the body up or down regulates the number of receptors? So it's pretty much the same mechanism at which it can upregulate or downregulate any type of protein throughout the body. So receptors are just different protein structures. And so it can either, it can, transcribe other proteins that will go and, you know, I guess, recycle the receptors we don't need anymore. It can completely go and destroy them, or it can just increase the amount of receptor present by expressing that gene. It can either shut off the gene and have things that will go and degrade the protein, or it can have things that can turn on and make more of that protein. Yeah, so it's essentially enzyme degradation. And we don't, if we want to downregulate, that is, if we want to downregulate, we'll degrade. Alrighty. So mechanisms of signal transduction. So the first mechanism of signal transduction, I know I'm going fast, I apologize, but we just have so many slides. The first mechanism is intracellular signaling. So if we have intracellular signaling, it must be a lipophilic messenger, which means it must be a steroid. So this will be a steroid signaling transduction pathway. So first we're going to have that messenger that's going to diffuse into the cell. It can bind to either one of two locations. You can have a cytoplasmic receptor, or it can have a nuclear receptor. If it has a cytoplasmic receptor, it'll bind to the cytoplasm. That now hormone receptor complex, the complex of both of them bound together, will travel into the nucleus, bind to a section of the DNA called the hormone response element. The hormone response element is different for every hormone. Let's say this is estrogen. Estrogen diffuses in, binds to the cytoplasmic receptor, comes in, and will bind to the estrogen response element. And this is an area where this hormone receptor complex will come, bind to this estrogen response element, and increase the production of that specific mRNA from that gene, and can create the proteins needed in response to that estrogen. But you can also have that, the hormone or the steroid hormone diffuse straight to the nucleus. And so it will have a nuclear receptor. The nuclear receptor does the same thing, creates that hormone receptor complex and binds to the hormone response element. And it alters what proteins are being expressed or what are not being expressed. So the question, can I relate how an increase in affinity or stronger binding, how can I relate that to hemoglobin? So if I go back to this, hemoglobin, if it has a stronger affinity, it's going to more tightly bind to the oxygen. And if it's going to tightly bind to the oxygen, it's not going to give it off to the tissues. It's not going to let the tissues have the oxygen. And if we have a lower affinity for, oxygen, if we're looking at the hemoglobin specifically, then it's not going to hold on as tight with a lower affinity. And so when it gets to the tissues, since it's not holding on as tight, it will kick it off to the tissues rather than hold on to it itself. And the physiological state, whether we're using oxygen or not using oxygen, can help dictate whether the hemoglobin will hold on to it versus not hold on to it. Alrighty. So in terms of signaling pathways and receptor activation, there are two terms that you need to be familiar with, and these are just jargon terms that will get thrown, get thrown at you left and right. So antagonist versus agonist. Agonist is anything that really initiates a positive response. So by activating, by upregulating, by doing anything that has a positive connotation, positive response, is an agonistic effect. An antagonistic effect is anything that does a negative response, downregulates, blocks, inhibits, shuts down. That would be antagonistic. And so you can see agonistic and antagonistic effects. So if we have an antagonist for a receptor, what it can do is it can block that receptor. It can block that signaling transduction pathway. If we have an agonist, it can activate that pathway, and the absence of the the desired hormone. So if we have, this, oops, I think I skipped this slide the first time around. Let's say we have, this pathway. If we just have an agonist that's present, it could possibly activate this pathway without that hormone ever being present. An antagonist can block this pathway even when that hormone is present. And so agonist versus antagonist are different jargon terms that will be thrown at you. Let's see. Need more people join. There is the PowerPoint. Cool. Okay, more mechanisms of signal transduction. So this is cell surface signaling. The first, we're looking at membrane-bound receptors. So the first type of receptor we're looking at is channel-linked receptors. So channel-linked receptors are when the messenger binds to the cell surface receptor, right? So this is probably going to be nonpolar. It's going to be, or sorry, it probably is going to be polar. It's going to be lipophobic. It would probably be a peptide hormone. It's going to signal at the cell surface. And when it binds to the receptor at the cell surface, it's going to cause a conformational change of that receptor. So our first example are the channel linked receptors. Why it's channel linked is because this receptor is also a channel. So the conformational change that will happen will be that this channel will either open or close depending on what type of channel it is. And so we can have things that can, you bind to it, opens up, and allows sodium to go through, potassium to go through, chloride to go through. And so if we think about this, so we look back at the nervous system structure, and we have those neurotransmitters that will come in, and it will bind to the dendritic arbor of the postsynaptic neuron. And what happens is the neurotransmitters will bind to this receptor. That receptor will open up, and it will either allow sodium through if it's an excitatory postsynaptic potential, or it can let chloride through if it's an inhibitory postsynaptic potential. So those are examples. And so if we're letting these guys through, what these channel link receptors can do, it can cause a change in membrane potential. So change in membrane potential can be that downstream signal. So as we see throughout the nerves, right, and neurons, the change in membrane potential reaches that threshold and we send an action potential. That signal will be propagated through that action potential. So it doesn't have to be specific hormones that signal all the way through. The hormone can be that initial primary messenger, and then depending on the cell type can do whatever it needs to do to propagate that signal. So one thing that channel linked receptors can do is they can change the membrane potential, and that change in membrane potential is how that signal will propagate. Something else that these channel linked receptors can do is they can allow in calcium. So what can calcium do? Calcium acts a lot of the time as a secondary messenger. So what does that mean? So we have that primary messenger, which is that hormone we're looking at. It'll come and bind to our membrane-bound receptor, or channel-linked receptor. And rather than having sodium, potassium, or chloride run through, it allows calcium to run through. And what calcium does is that calcium is now messaging to things inside the cell. So depending on the cell type, it can cause a change in electrical properties because yes, it is an ion. If we're in the muscles, it can cause contraction of the muscles. If we are also at, in a nerve, it can cause secretion of our neurotransmitters, right? But can also initiate a cascade. And what initiating a cascade will do is if we have that calcium flow through, that calcium is now going to bind to something else. It's going to be a messenger to something else because it's not the initial hormone, it is the secondary messenger. So in this case, the most common cascade it binds to calmodulin. So now you have calmodulin, which is just, you don't need to get focused down to the nitty gritty. I'm just trying to familiarize yourself with what a secondary cascade will look like. That calcium calmodulin complex will activate a protein kinase. And what a protein kinase does is it tacks on the phosphoryl group. So that phosphoryl group can now added to a protein could potentially cause a downstream response. So maybe that was an enzyme, and now that it's phosphorylated, that enzyme is now active. Maybe it was active when it was not phosphorylated, and phosphorylating it shuts down that pathway. What specifically this pathway does, it will differ from cell type to cell type. So not all calcium influx, pathways will respond the same. It changes from cell type to cell type throughout the body. So calcium is an excellent secondary messenger. So why is it a great secondary messenger? The first reason is that there are low concentrations in the cytosol. Why is that important? If we had high concentrations of calcium in the cytosol, then it would essentially always be signaling. What makes a messenger good is that it's not always present. It's only present in the needed, scenarios. And so what having very little calcium also does inside the cell is allows for a giant gradient. There's more calcium outside the cell than inside. So as that channel opens up, there will be that gradient causes for rapid signaling. The calcium will rush in. And so not only does it not signal because it's not present, but also when the primary messenger is there, it rushes in very, very rapidly. So how do we keep calcium low inside the cell? So we actively can shuttle it outside of the cell. We have calcium pumps that will kick it out of the cell, send it out into the extracellular space. We can tie up the calcium with proteins. So what I mean by that is the proteins will bind to the calcium. And because the calcium is not free floating, it's essentially tied up and not able to do anything. It's not able to signal. But also we have calcium that gets shuttled and stored in organelles. So it can be stored in the smooth endoplasmic reticulum. It could be stored in the mitochondria. If it's stored there, it's not free floating throughout the cytosol, not causing any downstream signaling. So not all membrane receptors are channels. They don't have to be. They can be enzymes themselves. And so we can have these receptors called enzyme-linked receptors. The most common that you'll see is shown here. It's called the tyrosine kinase receptor. What happens is as we have that hormone that will come in, it will bind to that receptor. That receptor will have a conformational change, but that conformational change isn't going to open up a channel. Rather, it'll activate its enzymatic activity. So as we see here, it's inactive. It's bound to its receptor, and that conformational change is going to cause the activity to turn on. So for a tyrosine kinase receptor, its enzyme activity is it's a kinase for tyrosine residues. So what does that mean? If we have a protein with a bunch of tyrosine residues, meaning that throughout that amino acid chain, throughout that protein, a lot of those amino acids are tyrosines, one or more. So what this receptor complex does is it'll come in and do what a kinase does, phosphorylates. It'll tack on phosphoryl groups to the tyrosine residues. So what does a tyrosine kinase do? It tacks on the phosphoryl groups to tyrosines. And so what happens is we're bound, enzyme activity is turned on. We phosphorylate the tyrosine residues on this protein. And now this phosphorylated protein can be turned on. So it can go on and do its enzymatic activity and cause its response downstream in the cell. So this initial hormone, the way its signal is being propagated is by turning on another protein inside the cell to do its dirty work. We also have G protein coupled receptors, or GPCRs. So a G protein coupled receptor it's a receptor that is coupled to a G protein. So this receptor, which is shown in green in this picture, isn't the G protein itself. The G protein is this heterotrimeric structure. What does heterotrimeric means? It means that there are 3 different subunits. So the three subunits are alpha, beta, and gamma. So every single G protein coupled receptor, so the receptor itself, has 7 transmembrane domains. So this is one of those things that if you see in a passage, it refers to 7 transmembrane domains, or if it asks you how many transmembrane domains does the GPCR have, the answer is 7. It's a conserved property. They all have 7. So what I mean by that, let's say we have our membrane as the protein itself, because the receptor itself is a protein. As it folds itself up and inserts it into the plasma membrane, it crosses the plasma membrane 7 times. 1, 2, 3, 4, 5, 6, 7. So it's folded itself up and it crosses the membrane 7 times. So 7 transmembrane domains. And our ligand will just bind right here. Sit on top and it'll activate it. So what happens when our GPCR binds to its ligand? So what's going to happen is we're at resting state. We're going to bind to the signaling molecule. The alpha subunit itself is going to kick off the GDP. So guanosine diphosphate. It's going to kick it off. And instead, what it's going to do is going to pick up a GTP, guanosine triphosphate. And so what that's going to do is that's going to cause the alpha subunit itself to dissociate from not only the GPCR, but the beta and the gamma subunits. This alpha subunit will migrate through the membrane over to, a neighboring, it could be channel, it could be a different enzyme. So we'll take a look at that here in a couple slides, but it's going to drift over and cause some sort of change, some sort of response. So that change will propagate a signal. Once it signals, the GTP will cleave off a phosphoryl group, hydrolyzes that GTP, turns it back into a GDP. So it's a GDP here. We kicked off one of those phosphoryl groups. And the alpha subunit is going to come back, reassociate with the GPCR, reassociate with the gamma and the beta subunits. So let's look at how that signaling transduction works. So this is one where the GPCR itself is associated with a channel. So we have that messenger that binds. It's going to cause the alpha subunit to kick off the GDP. It's going to pick up a GTP. It's going to migrate. The alpha subunit is going to migrate, and it's going to activate, in this case, a channel. That channel is going to allow ions to move in and out of a cell. So if we look at different types of channels we've talked about previously, and we look at cholinergic receptors. So cholinergic receptors are nicotinic and muscarinic. So nicotinic receptors look more like the ligand-gated channels we saw earlier. But the muscarinic cells, the muscarinic receptors, are GPCRs. So this would be an acetylcholine, and it would cause a response here. So, but if we look at cholinergic receptors themselves, nicotinic is ligand-gated, and muscarinic are G protein coupled receptors. Why is it good to have, if they're doing the same thing essentially to the same messenger, why is that good? G proteins are slower. They're slower to react, and they're slower to close. So they stay open a longer period of time. What this does is allows for variability and more control throughout the system. So our body can have fast channels and slow channels. And depending on what the property is of the different types of cells, we would prefer one over another. So this gives the body more options to create similar responses at different strengths, different intervals to the same types of hormones. And so that's why we have both nicotinic and muscarinic on an evolutionary basis. So we can also have, similar to the enzyme-linked receptors, G proteins that can regulate enzymes. And so what they do is they're really, well known. They're notorious for activating amplifier proteins. which means is as the G protein gets activated, the alpha subunit dissociates, and rather than activate a channel, it's going to activate an enzyme. And that enzyme initiates a cascade that's an amplifier. That means if we have one signal, we can create a giant downstream response. So I have an example here. So an example here, we have the GPCR. It binds, the alpha subunit is going to dissociate, and it will activate an adenylyl cyclase. So activating the adenylyl cyclase, we have one signal molecule, but it's going to create a giant cascade. And what a cascade is, we take one ATP, we turn it into 3 cyclic AMPs, and each of those cyclic AMPs can activate a protein kinase A. Each of those protein kinases can phosphorylate 3 proteins. So we just went right off the bat, one starting substrate to now we have 9. Each of these phosphorylated proteins can cause a bigger response. Each of those responses cause an even bigger response. So what a cascade does, an amplifier protein, such as the most notorious example, adenylyl cyclase, it can turn this one starting substrate into this giant cellular response. So the exponential increase on a stepwise process. So that is what an amplifier protein does. What is the significance of cyclic AMP or CAMP? In this case, for adenylyl cyclase, it's just one step in this amplifier protein, and it usually gets generated from ATP using adenylyl cyclase. This is just well, you see CAMP a lot in a lot of different places. And the reason why is because it's such a conserved and easy, I guess, structure to make that it can be a stepwise process in a lot of different amplifier protein cascades. And what it does, what it downstream it does depends on the cell type. So different cell types will cause different downstream response. Yeah, that's just very simple to do, very easy for the cell to make. But what it really does downstream just depends on the cell type. So G proteins don't directly activate a channel. They usually bind to something else. Yeah, so they don't directly activate any channel. What happens is you do have that alpha subunit that goes over and activates something else. That's how G protein coupled receptors work. It does. One example is amplifier protein. It doesn't always have to be an amplifier protein, but most likely it is. If it was an amplifier protein, they can essentially just do it would be very similar to an enzyme linked receptor. So why would you waste energy doing a GPCR instead of an enzyme linked receptor in that case? So most often the GPCRs will activate amplifier proteins because not only does it activate for longer, but it creates a stronger response. And so that gives the body examples. Can I provide an example where physiologically where one method is preferred over the other? Ooh, that is tough. Ooh, I mean, it really depends on the tissue types. I cannot think of off the top of my head where physiologically why one would be wanted over another. So I'm trying to think. I mean, in this case, if we just look at it without a specific example, why would we want one of these? Why would we want a GPCR rather than, let's say, just a typical tyrosine kinase receptor? Why would we want the adenylyl cyclase rather than a tyrosine kinase receptor? Is whatever that tissue type, whatever that cell type is. One, tyrosine kinase receptor might, on an evolutionary basis, might not cut it, and it might not give the strength of signal that we want in that tissue. And so it's been more beneficial to it to have been an amplifier protein in this case to create a giant response. I can't think of a specific tissue type on why it developed one over another. Alrighty. So summary of receptors. So does a receptor act at the membrane? If it acts at a membrane, it can be one of 3 types of things: channel linked, enzyme linked, or G protein. And those G proteins themselves can be linked to an enzyme where they can activate a channel. right? And then the channel linked receptors, what can they do? They can either create a change in membrane potential or be a calcium influx. If it binds at intracellular locations, where it's going to do, it's going to bind to the hormone response element, and it's going to change protein expression. So what is the difference from a tyrosine kinase enzyme receptor and the ligand receptors? So the tyrosine kinase receptor itself does bind to a ligand. So if we go back to it, where the heck did it go? So it does bind to a ligand. The ligand itself is a messenger. So you can interchangeably use the terms, messenger, hormone, ligand in this case, or even substrate. So the difference between what I think you're asking is enzyme linked, in this case, tyrosine kinase, is it binds to the ligand rather than opening up a channel. It has a conformational change, and this itself has enzymatic activity to cause downstream change. The ligand gated channels, so the full name of them is ligand gated channels. What they are is they're ligand gated, so the ligand binds and it opens up the channel. And this channel causes the flow of smaller particles, usually ions. Those ions themselves can cause electrical changes, change in membrane potential, right? It's because an open channel is going to change permeability, or it can open up for calcium. And that calcium can, because it is an ion, cause electrical changes, but it can also cause downstream signaling in other pathways as well. Does that make sense? I think that was your question was. Awesome. Okay. So, I think that was it for the nitty gritty of hormone signaling. So I'm gonna do a couple questions. We do have a passage at the very end that I feel is quite accurate, and that's one I like. So passage will be at the very end, but I'm just gonna do some quick questions here. How do steroid hormones differ from peptide hormones in their signal transduction pathway? I'll give you like 15, 30 seconds to answer this. Answer it in the chat. Awesome. Yeah. So how do steroid and peptide hormones differ in their signal transduction pathway? Right. Steroid hormones are lipophilic, so they can diffuse through the membrane. Peptide hormones are not. So peptide hormones primarily initiate signal from the membrane receptors. Steroid hormones diffuse into the cell. So it is C. Very cool. I think I accidentally sent out the slides in a direct message. So I'll do that again while you guys answer this one. Which of the following are considered antagonistic effects? Again, 15 seconds, 15:30. Alrighty. Very cool. So antagonistic is anything that has really a negative effect. So blocking membrane receptor activation, that's antagonistic. Inhibiting the release of peptides, that's antagonistic. And then blocking the upregulation is antagonistic as well. So it's 1, 2, and 4. And then which of the following occurs first as a result of GPCR activation? So what happens first as the G protein coupled receptor binds to the ligand? All right, so historically, I've had people choose between C and D. As soon as the GPCR binds to the ligand, the alpha subunit is going to kick off the GDP, exchange it for the GTP, and once it does that, then the alpha subunit dissociates from the beta and gamma subunits to initiate a response. So the very first thing that happens is that the GDP is exchanged for a GTP, and that's what causes the alpha subunit to dissociate. Alrighty, so that was, in my opinion, the unfun part of endocrinology. So we're going to get into the fun part now. Hormones. So briefly mentioned it last week, and maybe even a few weeks prior to that, the HPO axis. So this is where we get to kind of expand that. So hypothalamus, pituitary organ. So if you were to just take one slide away from today, study one slide, it would be this slide. So for what I study for the MCAT, I really am a visual learner. And I memorize things on a visual basis. So I stared at this picture for so long, I just made sure that it was kind of burned into my head, right? So this is the HPO axis. The hypothalamus releases hormones, and we'll go over what all these hormones do and what organs they send to. It releases these hypothalamic hormones onto the pituitary. The pituitary will then release hormones into the bloodstream to signal to their target organs. So if we're sending it into the bloodstream, how does it target specific organs? It's because these organs themselves are the only receptors that recognize these hormones. So if we have a the thyroid gland will have receptors that recognize TSH. But let's just say the adrenal cortex, it's not going to have receptors that recognize the TSH. So yes, it's being, sent into the bloodstream. And yes, the adrenal cortex is being exposed to TSH, but it's not going to respond to that. The reason why we have tissue specificity is because the target tissues are the only ones with the receptors to recognize it. So let's kind of sit here and break down this picture in a little bit more depth. So really, there's two parts of the pituitary gland. There's the anterior and the posterior pituitary gland. So let's start with the anterior. So at any given time, there are many hormones in the bloodstream. Absolutely. You have so many different hormones in the bloodstream right now. So you'll have all these guys in your bloodstream right now. And staring at this image, you probably have boatloads of this one. So we'll go into what this one does. Adrenocorticotropic hormone gets released in times of stress. So you probably have boatloads of ACTH in your system. But we'll go through that. Don't worry. So we have two sections of the pituitary, anterior, and posterior. So we're going to start with the anterior pituitary. In terms of looking at this, disregard median eminence. You're not going to need to know that. Let's try to limit the jargon that we need to focus on. So let's go with one that we recognize. This first one, GnRH, right? We talked about GnRH last week, gonadotropin releasing hormone. So the hypothalamus is going to release GnRH onto the anterior pituitary, and the pituitary itself is going to release FSH and LH. And the FSH and LH will signal to the gonads. If we look here, if we look at CRH, CRH is corticotropin releasing hormone. CRH is going to signal to the pituitary to release ACTH. ACTH is going to signal to the adrenal cortex. TRH is going to signal the pituitary to release TSH. TSH is going to signal to the thyroid. PRH, prolactin releasing hormone. For this case, I don't really want you to focus on these guys. We're going to look at the positive effects. PRH will signal to the pituitary to release prolactin. Prolactin will signal to the mammary glands. GHRH will signal to the pituitary, at least GH, or signals to the liver and all the rest of the body, because this is growth hormone. So we'll go over that. So, did any questions on how to kind of interpret what this chart is saying? These are the hypothalamic hormones getting released from the hypothalamus, signal on the pituitary. The pituitary releases this class of hormones, and these are our target organs, right? So HPO axis. Oof. TRH. Gosh, I forget what TRH. I think it's not thyroglobulin releasing hormone. I might be. TSH is thyroid stimulating hormone. In terms of what you need to know, is the more important ones you should know are these guys. So be familiar what TRH does, but in terms of what you need to know the full names of are the anterior pituitary hormones. So this is growth hormone releasing hormone, fantastically named. But we'll talk specifically of the anterior pituitary hormones. But if you see TRH, recognize, hey, that's going to release TSH, which is thyroid stimulating hormone. So what does that do? Well, it stimulates the thyroid. Let's see. So the key to memorize here are the hormones, where they signal, and their target organs. Bingo. Yes, yes. So I had 2 or 3 on my real MCAT. I had 2 or 3 hormone passages, which was disgusting. But what it was is they expected me to know this pathway off the top of my head, and they gave me in the passage. Let's say it was TRH. It was TRH antagonists, TSH agonists, and just I had to know this pathway and kind of add in antagonists and agonists on my little piece of whiteboard scratch paper thingy, to kind of keep it straight. Because this is what you need to know going into it, and if they add in agonists and antagonists, they'll be given to you. But as long as you kind of keep this straight, you can start to orient yourself. All right. So these are that's the anterior pituitary. Go backwards. Let's talk about the posterior. So the posterior pituitary only releases ADH and oxytocin. So if you look here, there's no hypothalamic hormones. What happens is there's just nerves that go straight from the hypothalamus to the anterior pituitary, and to the posterior pituitary, and the posterior pituitary makes and stores ADH and oxytocin. Something that's interesting between the anterior and posterior pituitary, the posterior pituitary stores these hormones. The anterior pituitary does not. As soon as GnRH signals to it, it's going to make and release FSH and LH. With the posterior pituitary, it'll make and store these hormones until needed. So that's something that's interesting about the posterior pituitary.
Quick question.
Is prolactin secretion in both males and females? It's mostly just females, but there are males where it does signal. It shouldn't be signaling. If it is, there's something going on there. Maybe there's some hormonal mess up, but typically we shouldn't. Was there a question? I heard someone unmute. Does dopamine and somatostatin inhibit PRH and GHRH? Yes, they do. So that's what that negative means. But in terms of what you need to memorize, I'm not too concerned about knowing that somatostatin and dopamine inhibit. We're only looking at the positive effects here. So if you're struggling on stuff you need to memorize, I would not focus on the dopamine and somatostatin part. But this was the most colorful and easiest image for me to memorize when I was studying. So that is why I included it. I love colors. So colors help me focus. But yeah, cool. let's look at what all of these do. This is the fun part. Very cool. So let's start with the posterior pituitary anti-diuretic hormone, ADH, also nicknamed vasopressin. So unfortunately, a lot of these hormones have many names, and they can throw these names at you and expect you to know them. Vasopressin is more of an outdated term, so you're more likely to see it written as ADH. Thank gosh. And so anti-diuretic is the opposite of diurese. So diurese is shedding water in terms of urine. So anti-diuretic hormone is going to make you, make the kidney more permeable to water. So you're going to hold on to the water rather than pee it out. And so why would you want to hold on to the water? It's likely more often not released in times of low blood pressure. So low blood pressure, if you absorb more water, you'll increase plasma volume. Increasing the plasma volume will increase the blood pressure. So when you drink alcohol, for those of you who do, alcohol suppresses ADH release. So that is why when you drink alcohol, you pee. You feel like you have to pee. It's because anti-diuretic hormone is being suppressed. Oxytocin is, as I said, a very, very versatile hormone. So in pregnancy, it binds to the uterine wall. It helps with contractions. It also, during pregnancy, to some extent, I know pregnancy is painful, but it does, in a sense, kind of numb the pain to an extent. Yeah, the pain's so much that you still feel it, but oxytocin dulls it to some extent. Oxytocin induces milk letdown. So in inducing milk letdown, that's the milk injection. The effects in males. So again, this is something that is being studied. It is something that is quite interesting. So it dulls pain in males as well. And so this is about to get not safe for work, R-rated. But during sexual intercourse, both males and females release oxytocin. And so that's why things that would typically be painful during coitus is not so painful. It just kind of dulls it to an extent. And also on a more psychological level, oxytocin is also a bonding hormone. So that's why, during, sexual relations, people feel more bonded to each other. It's because you're releasing oxytocin. During pregnancy, there's releasing a lot of oxytocin. And so mothers feel bonded to their babies. So it's quite an interesting hormone, oxytocin. It's very, very versatile. It does a lot of things and it needs to be studied more. That answer your question? There's a lot. So yeah. So these guys get released by the posterior pituitary. So anterior pituitary. Let's start with the growth hormone, also called somatotropin. You'll more likely see it written as growth hormone. It does what it's named after, what its name says, and what its name implies. It stimulates growth by increasing the rate of mitosis. It increases protein transcription, protein synthesis to increase cell size. It helps you break down fatty acids for energy and also mobilizes fat stores. So you can break that down as well. So it really helps with growth. There's a lot of growth hormone present in kids. So kids have a lot, right? Because they're growing. So if you're a bodybuilder, typically people will take HGH or human growth hormone. And what that does is that allows them to increase the rate of mitosis, burns fat, allows people to become bodybuilders. And it is for professional sports, it is a prohibited substance. You don't want to use it. ACTH, adrenocorticotropic hormone, signals from the anterior pituitary to. These are questions. Okay, never mind. Signals from the pituitary to the adrenal cortex. We'll talk about this more. We're going to zoom in on the adrenal cortex here shortly, but it gets released in times of stress. So right now, you're stressed, getting inundated with lots of hormonal information. So ACTH is being released and it is signaling the release of downstream hormones released by the adrenal cortex, which we'll get into here in like 2 slides. Thyroid stimulating hormone, TSH, acts on the thyroid to stimulate the release of T3 and T4. And so these guys really help with metabolism, energy, growth. Sometimes people with like childhood hypothyroidism will have stunted growth. So they'll be shorter. So like my dad had childhood hypothyroidism and he was like 5'2" in his senior year of high school. He started taking levothyroxine, which is like a T3 replacement, and now he's 5'8". And it's just his hypothyroidism kept him short. People who have hypothyroidism now feel lethargic. Like if you're older, if you're like, let's say in your 60s, have hypothyroidism, you feel lethargic, you always feel sleepy, no energy, weight gain. So typically when you actually look at blood work, when you look at labs, one thing that indicates hypothyroidism is elevated TSH. So if someone wants to say in the chat why elevated TSH levels means hypothyroidism, I would love to see if you can try to piece that together. Private chat if you don't feel comfortable. Why does elevated TSH indicate that we have hypothyroidism? I guess negative feedback is part of it. So that is an indication. And the reason why is it's because if the thyroid itself is not producing enough T3 and T4, then the anterior pituitary is going to feel like, shoot, that negative feedback is going to tell it there's not enough. And the low levels of T3 and T4 are going to make you release more TSH to compensate for the low levels of T3 and T4. So your T3 and T4 might be within normal limits, but your TSH is high, and your TSH being high is what keeps the T3 and T4 normal limits. So that is on like labs, that is something you might see in a passage. Hey, so think of it, downstream, if one of these are high, but everything's within normal limits, what does that mean? So if your T3 and T4 are within normal limits, but your TSH is high, they're within normal limits because the TSH is compensating. It's causing that to be within normal limits. It's causing more to be released. Say that once more, please. So yeah, you might get things that, let's say, if they'll give you, labs, let's say, TSH being high. So that in the HPO axis, so TRH is going to signal to the pituitary to release TSH, which signals to the thyroid. Thyroid releases T3 and T4. If everything's within normal limits, but let's say maybe TRH is a little bit elevated, TSH is a little bit elevated, where's the issue? So in that case, the issue is actually the thyroid, that it's not producing enough. So upstream, we've had to produce more to compensate for the downstream lack of functions, the downstream hypothyroidism. So yeah. Well, I'll give you another example when we get to in a kind of different context when we get to the next few slides. So these are ones that we've seen before. FSH, LH, and prolactin, right? FSH induces growth of ovarian follicles and also induces the development of sperm in the seminiferous tubules. Luteinizing hormone, if the spike, right, the surge induces puberty. During ovulation, it stimulates the release of the ovarian follicle, and it stimulates the release of estradiol and progesterone in females, and then testosterone in men. Prolactin is the milk production, right? Not milk letdown, not milk ejection. That is oxytocin. Oxytocin is the milk letdown, milk ejection. So parathyroid. So the parathyroid are these 4 little parafollicular glands on the back of the thyroid. And what this does, this is now where we get kind of separated from the HPO axis. The parathyroid gland measures and senses the amount of blood calcium, the amount of plasma calcium. And before we get on, what's the difference between prolactin and oxytocin again? Prolactin is milk production. Oxytocin is milk letdown or milk ejection. So prolactin is the production. Oxytocin is the ejection. So parathyroid hormone gets released in times of low blood calcium. So parathyroid hormone, PTH, increases blood calcium. So this parathyroid gland senses the concentration of calcium in the blood. If it's too low, it'll release PTH. If it is too high, we can release calcitonin, and calcitonin does the opposite of PTH. So there are three really, locations where we can try to adjust calcium in the blood. So we have calcium sinks in the bone. So if we need to increase our calcium in the blood, we can take calcium from the bone and put it in the blood. At the kidney level, we can choose to reabsorb more calcium rather than pee it out. And in the intestines, we can choose to absorb more calcium rather than excrete it out. So PTH acts on these locations to try to increase the amount of blood calcium. So what exactly does it do in the bones? So in the bones, there's three types of cells. So I'm going to type this in the chat. The first are osteoblasts. So osteoblasts build bone. Osteoblasts. So I typed it in the chat box. Osteoblast. That B blast builds bone, meaning it takes calcium and deposits it into the bone matrix. So what does that mean? So let's say we have a scaffold. We have this random bone scaffold right here. An osteoblast will come in, this osteoblast. It'll deposit calcium to create a matrix. And this matrix, these different matrices, are what create bone. Bone is a calcium matrix. So once an osteoblast finishes depositing all its calcium, it becomes an osteocyte. So let me write that into the chat. Osteocyte. So these osteocytes will just sit here and be essentially what we call nucleation sites. So a spot at which the calcium matrix can anchor. So the fact that it is anchoring to these osteocytes, the reformer osteoblasts, it allows the bone to not be so brittle, keeps it healthy, allows it to kind of deal with some different stresses, different forces. So these guys were all former osteoblasts that have deposited bone. And we're depositing calcium into the matrix and start building bone. So if we have a lot of calcium in the blood, we can essentially try to increase osteoblast activity, take that calcium and put it into bone. We have another type of cell, though, called osteoclasts. Type that in the chat. So osteoclasts catabolize bone or destroy it. Osteoclasts do the opposite of osteoblasts. So osteoclasts will come in and they will absorb the calcium from the bone and put it back into the blood. So osteoclasts, right, they catabolize, they break down the bone. They'll come in, they'll absorb that calcium, we'll recycle the osteocytes, and it's going to take that calcium and put it back into the blood. So if we have low blood calcium, PTH will be released, and PTH is going to increase the activity and the number of osteoclasts. PTH will increase osteoclast proliferation so that we can break down the bone tissue, take that calcium, put it back into the blood. So if we just happen to have two, let's say naturally we're in old age. In old age, our osteoclasts become too active. Osteoclasts become too active, we can start to have osteoporosis. Our bones aren't as becoming, they're becoming a little bit more, they're becoming less dense. They're becoming a little bit more brittle, a little bit more fragile. And so that's why when, elderly fall, they break bones so easy because their bone health isn't what it should be. The quality of bone, the osteoporosis has set in. And so we will talk actually at the end of the lecture, we have a passage about osteoclasts and blood calcium. So I think it's a great way to kind of apply this later on. Let's see. So clast cleaves and blast builds bones, exactly. So osteocyte absorption, what does that mean? That is a question. So these osteocytes are basically retired osteoblasts. So what it's going to be absorbed is basically, rather than just sit there now the calcium is being taken away, it'll be absorbed back into the body. The cells will be killed, they'll be recycled. They won't just sit there. They'll be brought back into the bloodstream and recycled. They are retired osteoblasts. So that's what happens in the bone with the calciums. So let's see, because I'm not Picasso. Okay, kidneys, right? PTH, if we have PTH gets released in times of low blood calcium, what's going to happen is it's going to tell the kidneys, hey, let's reabsorb more of the calcium in the proximal and distal convoluted tubules. And in the intestines, what's going to happen is we are going to absorb more calcium by increasing the steroids derived from vitamin D. So vitamin D is actually required to absorb calcium. So some people that have, osteoporosis, they don't have, too little of calcium into the blood, the body's going to resort to taking away from the bones to kind of tell the body, hey, don't do that. What we'll do is they'll give vitamin D supplements that will naturally increase calcium in the blood so that we don't have to take it away from the bones. If we absorb more calcium, wouldn't that take it out of the blood? Okay, yeah. So this is part always confuses you. So this is the tube within a tube system. If we are in the kidneys, if we are in the intestines, we're technically not inside the body. So if we are inside the intestinal lumen, we are technically outside of the body. So what I mean by absorb it is we absorb from the intestinal lumen back into the body, or absorb from the kidney tubules from that filtrate back into the kidneys so that we can bring it back into the blood. When you're in the blood, you're already in the body. But if you're inside the kidney tubules or inside the GI tract itself, you are outside of the body. All righty. Adrenal gland. So the adrenal gland releases steroids. So we've talked about one mineral corticoid, aldosterone, right? Aldosterone increases sodium reabsorption at the distal convoluted tubule, helps maintain saltwater balance. The adrenal gland also releases glucocorticoids, mainly cortisol. So cortisol is a fascinating steroid hormone. It can increase blood pressure by itself. So this is the stress hormone, right? Studying for the MCAT, cortisol levels are chronically increased, which is not good. So cortisol is needed. It does help with memory in low amounts. When you are running for your life and stressed, and you're releasing the ACTH, cortisol keeps your blood pressure from bottoming out. It keeps it high enough that you can get adequate blood flow. It increases gluconeogenesis so that you have adequate levels of glucose in your body ready for activity if you're, so let's say, running for your life. But by increasing gluconeogenesis, you are chronically raising blood glucose. So if you have a very stressful life and you have a lot of cortisol that is just chronically in your bloodstream, gluconeogenesis is going to be so upregulated so frequently that you're going to naturally just have a lot more blood glucose than you should have. And so cortisol can cause damage and that can lead to diabetes because of the high blood glucose if it's just chronically there. So that's why people with stressful lifestyles are at a higher predisposition for diabetes, because it can increases gluconeogenesis, increases blood glucose. So cortisol is quite needed. Something that is very interesting. Have you guys ever heard of prednisone? Prednisone is a oral medication that releases essentially it's a glucocorticoid, it's a steroid. It was originally used that if you were to have some issue with your adrenal cortex not functioning, you couldn't release the needed steroids. And so we used prednisone to kind of compensate for that. We found that prednisone is really good at suppressing the immune system and decreasing inflammation. So if we're using this steroid to suppress the immune system, why we want to do that? Autoimmune disorders, we want to suppress the immune system. It's autoimmune, but inflammation, chronic inflammation, that's not good as well. So it also suppresses that. But people who are on chronic uses of prednisone, that negative feedback shuts down your upstream, release of that ACTH. And so when you're in the hospital, typically you're stressed, right? If you're in the hospital, you're not going to be having a good time as a patient. And so people who are on chronic prednisone, that negative feedback loop has pretty much shut down their adrenal glands. And so what we have to do is basically give them a stress dose of prednisone. We have to essentially mimic their body being stressed out with higher levels of prednisone, because the body can't produce the cortisol it needs to due to that negative feedback. So that's quite interesting. There's a question, wait, can't the keto diet lead to higher chance of diabetes if the body isn't used to eating carbs and stuff? I mean, I suppose so, but keto diet is where you don't want to have any glucose in your bloodstream. So just being chronically on keto, it might not cause diabetes, but if you go keto and then start eating a lot of carbs and stuff, you can, but diabetes is something that happens more on a chronic level than on acute levels. So I don't know too much about keto actually leading to diabetes. We'll talk about diabetes here in a couple slides, but you need less cortisone. Yes, we all need less cortisol in our bodies. It is bad. Stress is not good. Something else that the adrenal gland releases is it releases the catecholamines epinephrine or norepinephrine. So when you're stressed the heck out or scared, you're stressed, the ACTH will signal to the adrenal gland. The adrenal gland releases that epinephrine and norepinephrine, those fight or flight responses. The adrenal gland also releases some trace androgens. What I mean by that is estrogen, testosterone. So yes, the gonads do release most of the estrogens and testosterone, but the adrenal gland does so as well. So another endocrine gland is the pancreas. The pancreas can release glucagon or insulin. So glucagon is secreted when you're starving, when you're fasting. So when you have low levels of blood glucose, you can release glucagon, which can stimulate protein and fat breakdown. It can take glycogen, which is the stored glucose, and use it for energy. Insulin is the opposite of glucagon. When you have high levels of blood glucose, insulin tells the cells of your body to bring it into your cells, take it out of the blood, use it for energy. So insulin is kind of the basis of where diabetes kind of sits around. There's two types of diabetes. There's type 1 diabetes and type 2 diabetes. Type 1 diabetes is an autoimmune disorder, typically. So where the beta cells that produce the insulin are attacked by your immune system. And being attacked by your immune system, they can no longer produce insulin. So type 1 diabetes are people who can't produce their own insulin, so they have high blood sugar chronically. So they need to take insulin to tell the body, hey, bring it into the cells, use it. If you take insulin without eating, if you're type 1 diabetic, then you don't have the blood glucose there. And so the trace glucose that is around will be taken in because insulin is saying, hey, take this blood glucose in. And it can cause dangerous hypoglycemia, where the blood sugar drops in your body. Your brain no longer has the glucose energy to function. You start having a lot of psychogenic reactions, dizzy, headache, altered level of consciousness, that type of stuff. And then, so glucagon gets produced by alpha cells, insulin by beta cells. So yes, autoimmune, a lot of times your body attacks the beta cells, can't produce the insulin, leads to type 1 diabetes. Type 2 diabetes is if you have a poor diet and you eat so much sugar, so much junk food that over a long period of time that you have a lot of blood, you have high blood glucose, blood sugar all the time. So your beta cells are working overtime saying, hey, more insulin, more insulin, more insulin. The cells of your body end up saying, oh, why are we always signaling for insulin? And so it becomes insulin resistant. We are going to downregulate the insulin receptors on our cells. We're going to start to ignore that signal. It's always there. So it's going to be like, why is the signal always there? So if we stop our cells stop listening to the insulin signal, we'll stop using the glucose, and the glucose will travel throughout the blood and just stay there, and it will stay there. So we have to take medications like metformin. So metformin is a medication that tells these cells that were previously insulin resistant to start being a little bit more resistant. If you are a type 2 diabetic that is uncontrolled for so long that your cells are becoming insulin resistant, so your beta cells need to produce more insulin to try to overcome that. So it's going to try to produce more to tell these cells that, hey, yeah, we do need to listen, stop ignoring me. You can eventually wear out your beta cells. If you wear them out, not only are you not producing insulin, but you're also insulin resistant. So you become very big trouble. So that's where a lot of diabetic complications come in. Yeah, so type 2 diabetes is reversible to a certain degree in the right diet. So if you change your diet and improve it, you can get these cells to start listening again. So what actually on my real MCAT, I had a diabetes passage in my psych soc section because it was talking about lifestyle changes and getting people to change the lifestyle, that type of stuff. When did you go over alpha and beta cells? Never actually went over alpha and beta cells. Alpha cells aren't something that I worry too much about. They produce the glucagon, but beta cells are more important. So right now is going over beta cells. Beta cells are release insulin, and so you can cause autoimmune issues to that and destroy your beta cells. How do you treat type 2 if it's insulin resistant? So both localized pancreas, yeah. So how do we treat type 2 if it's insulin resistant? Typically metformin, so there's medications that you can use that will increase insulin sensitivity. But let's say, if you can't actually, if you stop producing the insulin because you wore out your beta cells because you were just so uncontrolled for so long. So you're not only, you're resistant, but you can't produce it, you become big trouble. So that is when a lot of diabetic complications go out of control and not too great of a prognosis. Then we also have the pineal gland. So pineal gland is kind of separate of the HPO axis as well. The pineal gland is responsible for releasing melatonin. So melatonin is it helps your brain align its circadian rhythm. So melatonin itself does not make you sleepy. If you were to sit there and take melatonin and sit in a room that is well lit and you're staring at your computer, melatonin isn't going to do diddly squat for you. Melatonin only works if you use it and go lay in a dark room. And it's going to tell the body, oh, it's a dark cycle, it's time to sleep. So that is the best way to get, that is the how to use melatonin to the most effective way possible. It gets released by the pineal gland in response to dark periods so that your body can align itself with a circadian rhythm. So quick questions. Which of the following hormones are released from the posterior pituitary? It's only 2 of them, remember? All right, I'm not gonna wait too long because we need to keep going. It is B, right? Oxytocin, ADH, posterior pituitary. All the rest get released from the anterior pituitary. And last question here, which of the following includes functions of hormones released by the adrenal gland? Brilliant, brilliant, right? 1 maintains saltwater homeostasis. That's aldosterone. That does get released by the adrenal gland. 2, hormones released in response to stress. Well, that is both your catecholamines and your glucocorticoids, so like your cortisol. So that is also adrenal gland. 3, hormones released in response to T3 and T4. No, so T3 and T4 get released by the thyroid. The thyroid has nothing to do with the adrenal gland. And then 4, maintains uterine contractions during pregnancy. Nope, that is oxytocin. So which get released by the adrenal gland? 1 and 2. Okay, sorry for going so fast. There's just so much information. If you have any questions at the end, I will stay and answer those. Immunology is hard. This is one of my favorite classes throughout my undergraduate degree. Also, sadly, my lowest grade, but still super fascinating. But luckily for the MCAT, we don't need to know it in that depth. And you don't need to be experts. So pretty much what we learn here for immunology, what you need to know for the MCAT is like just the first week of that course. So this isn't something that we need to focus too much on, but I do want to familiarize you with the different types of cells and just the generic response pathways of the immune system. And at the very end of this, we do have a passage. So I could probably get this done in about 30 minutes. And so we should finish the normal lecture on time. But let's not waste any more time. Immunology. So what you need to know is we're going to innate versus adaptive. So we're going to look at the adaptive immune cells, innate immune cells, the different tissues with an immune function, the concept of antigen and antibody, how antigens present, how our cells recognize that, what an antibody is, how the structure of that as well, and how the major histocompatibility complex, or the MHC, comes into play. So these are all, I know, zoom. We're not going to focus too in depth on this, but there's a lot of stuff that you need to know. Just be familiarized with jargon and terms. So what is the general purpose of the immune system? Protection, right? The immune system is there to protect you from everything. There's 2 major branches, as I said. There's the innate and the adaptive. So we're going to start off with the innate today. The innate immune system is fast and non-specific. So what I mean by fast is as soon as something that's kind of there to harm you, gets exposed to you, your innate immune system will kick in. The very first part of the innate immune system is the skin. So the skin is a barrier between you and all the pathogens and toxins you bathe in on a daily basis. So injuries to this tissue, injuries to the skin, lead to inflammation. So you realize when you cut yourself, that cut gets swollen and a little bit warm and it's a little bit inflamed. What that is, it's an immune response. Inflammation is an immune response. What it's going to do is it's going to cause a barrier to form between the exposed tissues and the healthy tissues. It's going to try to sequester and trap any sort of infection, any sort of non-self, pathogens that have just been exposed to your open skin. So inflammation is an immune response. We'll talk about what the heat is here shortly. So these are all structures inside the body that have an immune response. So we talked about in the respiratory system, we do have mucus and cilia. Your lungs are the barriers to the world. You breathe in fungal spores, you breathe in bacteria, you breathe in nasty stuff all day long. And so what's going to happen is it comes in a healthy person, the mucus will kick it, will trap it, and the cilia will kick it up and allow you to cough it up. You also have some macrophages, which are white blood cells that exist there. And so these white blood cells will attack pathogens in your respiratory tract and throughout your bloodstream together. So we'll go over those in more depth today. The spleen helps with bacterial infections. It also helps recycle red blood cells. Lymph nodes store a lot of lymphocytes or a lot of your adaptive immune system cells. So when you do have infections, your lymph nodes can become swollen because your immune system's trying to increase the amount of lymphocytes present to help fight that infection. As we said, skin is that a barrier between you and those pathogens trying to harm you. And then the stomach and intestines, they also have an immune function, right? As you eat food, maybe the food has a bacteria on it, maybe it has E. coli on it, depending on what it is. Not ideal, not a tasty thought, but it happens. The stomach acid can denature and destroy bacteria on those foods. So there is a immune function to the stomach as well. So how does the body recognize what's foreign? And so what we actually recognize is an antigen. So an antigen is any structure that can induce an immune response. And antigens can be either self or non-self. So if we have a self antigen, it's usually just a part of a protein that exists, part of our body, it's our self, it's native to the body. The body's not going to react to it. But then there's non-self. So if you have non-self antigens, these are, could be a piece of a pollen, part of dust. So a lot of people are allergic to dust mites, also called dermatophagoides. Great name. It could be, very, I guess, let's be very topical, and it could be the COVID antigen, right? So that is non-self. It's a piece of that COVID virus that's not part of yourself. So your body's going to react to that. Yeah, so antigens are not non-self only. You can have self antigens as well. So that was a question in the chat. Very cool. So how do we recognize what's foreign? Let's keep on going. Let's say we have a non-self antigen. So non-self antigens, our body recognizes it. And let's say we have one little immune cell that recognizes it. Well, one little immune cell is going to freak out. It's going to be like, oh, I need more friends over here. I need more teammates. So we're going to release these substances called cytokines. So cytokines are molecules that, they can do a lot of different things. It can cell traffic. So it can bring over more immune cells to the area to help. It can cause vasodilation. So that's what causes the redness and the flushing of your skin. The vasodilation to basically open up the highway to bring in more immune cells. You can also have things like chemokines. And these, what they can do is they can locally increase the temperature and cause this little feeling of heat. And so these cytokines can do vasodilation, increase the local heat, causes inflammation, do a lot of different things, not only sequester an infection, but bring more immune cells in. So these are chemicals that help signal and initiate a greater innate immune system response. So when we bring over these innate immune cells, what do they actually do? So a lot of these innate immune cells are phagocytes, meaning they're eating cells. So phagocytosis is eating. So we have the virus or any sort of non-self antigen that we can ingest it and destroy it. So, right, macrophages are one type of cell that can perform phagocytosis. It's literally just eating foreign material to destroy it. We can also, if we're trying to recycle our own material, we can also phagocytose self cells to try to not only destroy but also recycle the material. So we can do that to ourselves, but mainly in a sort of immune system, picture, if we're looking at through an immune system lens, it's used to destroy these pathogens. How do these macrophages, these other phagocytes, recognize what is self, what is non-self? So yeah, let's say it's being brought over via cytokines, being brought over via chemokines. But when it gets to the area, how does it know? It doesn't have eyes. It can't look at it and say, hey, you're non-self, I'm going to destroy you. So we're going to go over different ways. The first is opsonization. So opsonization is a very complicated cascade, which you don't need to know the cascade. The cascade is beyond the scope of the MCAT, thank gosh. But what happens downstream of this cascade is we tag these bacterium with substances called C3b. C3b acts as an opsonin. So what an opsonin is, it basically is this tag. It says, hey, this is a non-self bacterium, and I'm going to tag you so when a macrophage or any sort of phagocyte comes in the area, it knows that you're the non-self and it can ingest it. So the C3b can be recognized by different receptors on the macrophage, but it also says, hey, let's tag it with antibodies that may be floating throughout the bloodstream as well. So what a C3b opsonization is it's one method of saying, hey, let's tag this guy. Let's tag it so we can recognize it, so we can induce phagocytosis. Another one, so very similar, you'll see is there's a lot of redundancy. We have these things called scavenger receptors. So let's say this bacterium or this pathogen evaded opsonization. So it doesn't have to be necessarily in this order either. This could have happened first, where we have these things called scavenger receptors on our phagocytes. Scavenger receptors recognize PAMPs, or pathogen-associated molecular patterns. These are conserved molecular patterns, conserved structures that exist on pathogens and not our own cells. So if a scavenger receptor, recognizes this typically conserved non-self molecular structure, it's going to know right off the bat, like, hey, this doesn't exist in the body. This is non-self. Let's ingest it. Let's destroy it. So firstly, we have opsonization, where we could tag it. We have scavenger receptors that recognize PAMPs, or pathogen-associated molecular patterns. Now we have toll-like receptors. Toll-like receptors are similar. They recognize these structures that are very, very rare in our body. For example, double-stranded RNA. So toll-like receptor, TLR3, recognizes double-stranded RNA. If it sees double-stranded RNA, it's like, wait, we only have single-stranded RNA in our body. So that's not good. Let's get rid of that. It has flagellin. So we don't typically have flagellin in our body either. So that is typical of a pathogen. Toll-like receptor 5. TLR5 will recognize that and say, hey, this is a non-self structure. We need to ingest it. So knowing, what type of structure it is, what TLR gets activated, we can try to bring in, we can secrete different type of cytokines, different chemokines to bring in the necessary guys to come fight. But very similar, these guys recognize non-self structures and tell the phagocytes to eat it up. Then lastly are antibodies. So we do have antibodies that will exist on the phagocyte surface, and they can very similarly recognize specific structures like TLRs do. You can also have antibodies that float throughout the body, so humoral antibodies, and we'll talk about that in a bit. But they also are a different way of tagging these non-selves for ingestion. So it really just seems like the last 4 slides were very similar ways of doing the same thing. So that's a lot of redundancy. And so the reason why we do have redundancy is so that these bacteria and stuff, they get caught and they're not allowed to run wild. They're not allowed to run free, unchecked, and cause issues. So our immune system is really well developed. it's quite ingenious what the immune system can do, so that we try to avoid things from, causing us sickness. We get exposed to so many things on a daily basis, but our body can knock it down real fast. So once we do recognize it, how does it work? How does phagocytosis work? So the first is that physical contact or the binding. It binds to the scavenger receptor. The CR1 receptor recognizes the CD3B. We have maybe the antibodies on the phagocyte surface, or we do have TLRs or whatever, if I didn't say TLR already. But we bind, so that's the first step, physical contact, binding. Then we have ingestion. So these pseudopods will extend out and basically, like a mouth, gobble up around that pathogen. That pathogen gets brought into the cell, but that cell's not infected. It's sequestered in a phagosome. So it's not it's not in the cell. It's not allowed to run wild. It's basically under arrest. It's under arrest inside that cell, not allowed to do anything. It's going to fuse with a lysosome. The lysosome is going to have a lot of digestive enzymes, and it can lower the pH. So as the lysosome fuses with this now phagosome, it becomes the phagolysosome. And so the phagolysosome will have these degradative enzymes, and we're going to lower the pH, and we're going to completely digest this bacteria or this pathogen. We're not going to let it exist. We're going to completely get rid of it. We're going to make sure it's dead, not able to infect our body. After we have that, that went up, we have this structure called the residual body. So everything is neutralized. The pH, it was lowered. It's now neutral. Everything's already digested. It's not a full pathogen anymore. We're going to just then, after the residual body, release it into the bloodstream, and we can just get rid of it like any other protein structure, as if it's essentially just these random proteins floating around. That is one method. So other cells of the innate immune system. So white blood cells, there's more than one white blood cell. There's a bunch of them. So the first is mast cells. So when activated, right, they release a lot of cytokines. And what cytokines can do is they induce an inflammatory cascade. So some of those cytokines are histamines. So blood vessel dilation becomes super red. Why did we have dilation? To increase the blood flow, get that highway working. So when you do take antihistamines like loratadine, also known as Claritin, what you're doing is you're essentially trying to inhibit these histamine actions so that you don't have the swelling of the nostrils, where you get plugged, nasal cavities, where you don't get the itchy eyes, you don't get the runny nose, because those are allergies, right? What those allergies are is just the histamines going and doing their thing. It's all these different type of things getting released from mast cells. So you can have issues with mastocytosis. I had a patient once that had mastocytosis, which is really a large amount of mast cells. So any sort of non-self thing that got into her, her airways, it triggered a large scale mast cell activation. And she pretty much went into anaphylaxis multiple times per day. As a kid, she was telling me that she was maintained on, 5 EpiPens a day, and that is expensive. So now what she does is she has a PICC line, or basically a peripherally inserted central catheter, where she injects antihistamines straight into her bloodstream multiple times a day. Saves money, but it keeps this response at a minimum. You also have neutrophils. So neutrophils are the most abundant of the white blood cell. They are phagocytic cells. They can digest and eat non-self stuff. They release granules. They're granulocytes. What these granules do is that they are toxic to the bacteria, can kill them. There are proteins called defensins. Defensins is a fantastic name. I think are very cool. They're basically they're dimeric proteins that can insert themselves into a bacterial cell wall, and then they separate themselves. So after they insert themselves into a cell wall, they separate themselves and cause a gap in the cell wall, cause that bacteria to rupture and pop, and essentially kills it. So as I said, neutrophils are the most abundant for our white blood cells. Eosinophils target multicellular parasites, but what they're really well known for is inflammation. So one of the phenotypes of asthma, there's really two main types of asthma. IgE phenotype, which is allergic phenotype where allergies can trigger that, that inflammation response, but also eosinophilic asthma. So there's eosinophilic asthma and eosinophilic gastroenteritis, so in the GI tract as well. If you have too many eosinophils, you can cause way too much inflammation. So that's what the eosinophils do, is they really moderate and create inflammation as needed. But obviously, too much of them can cause issues. Inflammation is not pleasant in our body. Eosinophils, if you ever have some sort of H&E staining, this is not really something that will pop up on an MCAT, but they are known for their bilobes nucleus. They look like that. Eosinophils are, if you do have staining, look very, very unique. What we need to know is, hey, these guys are really good at inflammation. And basophils, there's another type. They release heparin. So what heparin does is it keeps the blood from coagulating. So when you do need that blood flow trafficking, you need the blood to keep going to the area so you can bring in more immune cells. These guys keep that blood flowing. They keep it from clotting. So it releases that heparin as an anticoagulant. We also have types of cells called dendritic cells, and these are a type of antigen presenting cells. So what we can do is we can actually degrade antigens. And when we degrade these antigens, we could take pieces of them and present it to our adaptive immunity. So we'll get into that. We'll get into how it presents it. And when they present to our adaptive immunity, it's basically teaching our adaptive immune system, because we're still in the innate immune system right now. It'll teach the very specific adaptive immune system, hey, this is our infection. You need to create soldiers to target this specific infection. So these antigen presenting cells are the bridge between innate and adaptive. It can digest things because they are phagocytic, but it can take what it digested and present it to the adaptive immune system and say, hey, this is in the body, search for it, kill it. Oops. So this isn't something I need you to focus on too much. This is just to show you all these cells in the blood came from hematopoietic stem cells. So they came from the bone marrow. And so if we look here, red blood cells had a common ancestor with all of these white blood cells. I always thought that was something that was very fascinating. They had a very, they had a common stem cell. And it was just basically differentiation, and the niche in which it developed turned things into a red blood cell versus a neutrophil versus eosinophil. So they all came from the hematopoietic stem cells from the bone marrow. So where do these white blood cells come from? They get produced in the bone marrow. The adaptive immune system. So the adaptive immune system is very, very specific, and we'll get into how it is. But it takes much longer than the innate immune system. It can't, create a response as fast as our innate immune cells can. But it's very specific, and it learns what it needs to attack, and it stays around for a longer period of time. So that's why it's also called the acquired immunity, because it learns itself. You have to be infected for it to be developed, and it kind of has a memory as well. So these guys, they kind of kick in much later than the innate immune system, but they're more specific and can last a longer time. It can protect you over a longer period of time. There's two major populations of cells in the adaptive immune system. The first is B cells. So why are they called B cells? Is because they mature in the bone marrow. So they're always called naive B cells. They get transported into the lymphatic system and go into the blood and circulate throughout the body. So they're naive because each B cell has a B cell receptor, which we'll talk about in the next slide, that it's very specific to a certain antigen. It doesn't know what it's looking for. It has a receptor. It's just floating around until its receptor matches to its antigen. When it matches its antigen, it can mature into either a plasma cell or a memory B cell. And so we'll get into what that is here shortly. So The naive B cell, once it encounters its antigen, it matures. So each B cell has what is essentially an antibody structure on it. So antibodies have two major chains. It has two heavy chains, which are these longer guys, and light chains. So antibodies, we'll get into this in a second with humoral immunity, have the same structure. These B cell receptors have very unique receptors on the end. And so they exist on these B cells to encounter their antigen. Let's say this B cell encounters this magenta. That's not even magenta. Whatever color that antigen is, it's not going to do anything. It encounters this green antigen, not going to do anything. Same with this red one, not going to do anything. So that's why it's called naive. It's a B cell, but it doesn't really know what it's doing. It encounters its yellow antigen, and it's like, ooh, okay, this is what I'm made for. It's time to do work. So it can do two things to mature. It can ingest, it can kind of bring in this antibody and start to produce tons of them. It produces tons of this specific antibody and injects it into the bloodstream. When it produces this specific antibody and you have this antibody now into the bloodstream, this antibody is floating throughout and can now tag all of these non-self antigens, these very specific antigens for the innate immune system to find. Maybe this antigen was evading that innate immune system. The innate immune system couldn't recognize it. But now that this B cell has recognized it and it can now tag it with all these antibodies, the innate immune system can find it no problem. So that's called humoral immunity. Where did my drawing tool go? That's humoral immunity. When we do have that B cell encounter it, we're going to produce all these antibodies so that as soon as that non-self gets in, it's tagged. So why is it called humoral? Is because blood was one of the original four humors developed, kind of hypothesized by the time of Galen back in ancient Rome. It's kind of that type of name, but we have all these antibodies floating throughout. So, when we do have things like this, vaccines, this COVID vaccine, how does it work? This COVID vaccine, it's this mRNA, right? What's going to do is it's going to trick the body into producing an inert part of the COVID virus, inert protein, specifically the spike protein of the COVID virus. That is going to it's going to activate the B cell specific to that random antigen. And what's going to happen is that B cell is going to take in that, that B cell receptor and create all these different antibodies, these IgGs, these IgMs, these different antibodies, so that when you do actually encounter the real virus, it's tagged rather than having it being able to proliferate no problem. So it's an artificial active immunity. Yeah, so we essentially trick the body into creating an adaptive immune response, even though we haven't encountered it yet. So there's a question. So the B cells have an antibody at the surface, but to start, yes. So there's a question. So before primary exposure, there are already antibodies for the pathogens, but very minimal. So it's not, so exactly. So the reason why it already has the antibodies for these pathogens, it undergoes rearrangement. So there are essentially almost an infinite assortment. There's, billions of different types of possible combinations of these B cell receptors. And it just happens that these B cells encounter their antigen. So that's why it takes so long for the adaptive immune system to kick in, right? It's not going to initially encounter its antigen. Only with luck and time will it encounter its antigen. And so what it's also going to do, what I mean by differentiation, another way it can react is you can cause proliferation and differentiation of these B cells. Basically, what you can do is you can cause these B cells to proliferate and cause a bunch of them. They're no longer the naive B cells. They're no longer naive. They encountered what they need to encounter. So they can create many, many, many versions of this B cell. So you get this proliferation, get tons of B lymphocytes. That's why your lymph nodes become a little bit engorged, a little bit swollen, because you have so many of these guys now. And it becomes memory B cells. So that's not even differentiation. It's now no longer naive. It takes its next step. It's memory B cells. It's there. There's a bunch of them. It knows that, hey, this antigen's there. So I'm going to send these B cells all over the place to go find it and tag it. That's how B cells work. What about T cells? So T cells, they also mature in the bone marrow, but they also go and finish off their differentiation and their maturation in the thymus. So that is why they are called T cells. So in the thymus, they gain their CD4 or CD8 receptors. So what are these? Let's get into that. The type of receptor, either CD4 or CD8, will tell you what this T cell recognizes, what it does. So T cells also have rearrangement. They have a lot of different variations of the T cell receptor binding site. There is rearrangement is one of those buzzwords on how you create such a diverse variety of these receptors. So it allows large binding diversity. So you can recognize as many different types of antigens as possible. But what these T cell receptors also do is they recognize MHCs, major histocompatibility complexes. And what these MHCs do is they present, digested antigens on the cell surface. If it's a self antigen, we know it's not infected. But if it's a non-self antigen that the MHC shows, we know, hey, there's an infection somewhere. There's something non-self in the body. So the type of MHC also can tell you where this protein was derived. So there's two types of MHCs, class 1 and class 2. So class 1 MHCs show antigens, either self or non-self, that were derived from inside the cell itself, from intracellular antigens. It can be a virus, bacteria that exists inside your cell, or something that's non-self, or something that is self that they took from inside your cell as well. So they're structurally different, class 1 and class 2 molecules. And so the body can recognize that. We'll get into that here shortly as well. But if we present something on a class 1 molecule, it tells our T cells, this peptide or this antigen was derived from inside the cell. So if it was derived from inside the cell via the endogenous pathway, which we'll go over here shortly as well, we know that this came from inside the cell. So if it's a non-self, it's infected. If it's a self, it's just going to ignore. It's like there's no infection here. But if we derive it from if we see it on a class 2 molecule, it's telling the T cells, it's derived from the exogenous pathway. It's telling T cells, it didn't come from inside me. It's not actually infecting inside me. This is something I digested. So a phagocyte that digested something, right? It takes a piece of that protein or piece of the peptide of that non-self antigen from the residual body, presents it on a class 2 molecule and says, hey, I just digested this. If it's a non-self, it says, okay, I just digested this infection. It's somewhere else. But if it's something that's self, the T cells, you're like, oh, there's no infection here. This is a self peptide. We can ignore it. So what are these different pathways? So endogenous versus exogenous pathway. So an endogenous pathway is that antigen is already inside the cell. The cell, whatever it is infected. The exogenous pathway, it underwent phagocytosis. So it's not actually infecting the cell. The cell brought it in and it's isolated in a phagosome. So after, you bring it in, or if it's already in, we're going to process the antigen. So what's going to happen is that virus or bacteria will create viral or bacterial peptides. We'll take those peptides, process them in the endoplasmic reticulum, and present it on the cell surface. Now, if this is an infected cell, it can present non-self peptides, but for any just normal cell, it will present peptides that get processed in the endoplasmic reticulum on the cell surface. If it's a self peptide, we'll ignore it. But if it's a non-self, it says, hey, I'm infected. For the exogenous pathway, we're going to digest it. Whatever we digested, again, we presented on the cell surface. When we present it on the cell surface, it's going to tell these cells, hey, this is what I just digested. If it's self, we're going to ignore. If it's non-self, we're going to say, hey, there's an infection somewhere. I know you're not infected because you presented on an MHC class 2. So let's find this infection. So that is how MHCs work. So how do we actually create these T cell selections? So there's different processes these T cells need to undergo to make sure that they function properly. The first is positive selection. So you can read this as a lot of words. What positive selection pretty much is it makes sure that these T cells can recognize self-MHCs. If it's going to be presented about 6 MHC class 1s, 6 MHC class 2s, and it's going to make sure this T cell receptor recognizes that it's self. If it acts as if this MHC is non-self, we'll destroy it. So about 98% of all T cells that get produced in the bone marrow go to mature in the thymus. About 98% of them will be destroyed because they accidentally recognized one of these MHCs as a non-self. If you do that, that can lead to autoimmune issues. If it recognizes self as non-self, that can create an autoimmune issue. So if they fail, they apoptose. About 98% of them apoptose at this point. After positive selection, they undergo negative selection. So negative selection does a couple things. Negative selection will basically differentiate if they have a CD4 or CD8 receptor. So it tells them what type of T cell they'll be. We'll go into those receptors here shortly. But it also makes sure that, yes, it does recognize self-MHC, but it doesn't bind too strongly. So negative selection makes sure that we don't bind too strongly to self-MHC. If we do that, we can accidentally have autoimmune issues as well. So put simply, positive selection makes T cells recognize self-MHC. Negative selection, yes, recognize them, but don't bind too strongly. CD8, CD4 T cells. So the main two you need to know are CD4, CD8. You also have CD25, which I'm not too worried about you knowing, but I do have that just shown here just in case. CD4 T cells are also called helper T cells. CD4 T cells recognize MHC class 2. Why are they called helper T cells? Because they don't actually do anything other than, hey, it recognizes that it's something on MHC class 2. It's not going to kill that cell because it's not infected. But what it's going to help do is it's going to help bring more immune cells into the area to help fight whatever infection it is. CD8 T cells are called cytotoxic T cells. CD8 T cells recognize MHC class 1s. So if a non-self peptide is presented on an MHC class 1, we know that the cell that it recognizes presenting on MHC class 1 is infected itself. So at a CD8 T cell recognizes MHC class 1, this cell is infected. The cytotoxic CD8 cell can kill it. So CD8 cells have the ability to destroy infected cells. So that is why the CD4 recognized MHC class 2, because it doesn't need to kill the cells. It just needs to help sequester more immune cells into the area. While the CD8 cytotoxic T cells recognize MHC class 1s, it can potentially recognize infected cells and it can kill them rather than allow whatever pathogen it is to utilize that cell's machinery. That's the difference between CD4 and CD8 T cells. So in kind of summary, innate versus adaptive. Innate immune cells, fast. They happen within minutes, hours. The adaptive happens slow, within days, right? We need to actually have the adaptive immune system encounter a pathogen. So it's very specific. It looks for a very specific antigen. It needs to actually encounter that. So that's not going to happen immediately. So that's why the adaptive immune system takes so long. But you do need both. You need both innate and adaptive. If you only had innate, let's say something overwhelmed the innate immune system, that infection can take over and potentially be fatal. If we only have adaptive, then that infection can get so widespread before the adaptive immune system even kicks in that it's also fatal. So you need both. You need that innate immune system to slow it down, but you need that adaptive immunity to come in after it's slowed down and actually wipe it out. So you need both of them. They work together to create a fully prepared response to whatever infection it is. So that is essentially, you don't need to know immunology in too much. So they can go way deeper than what we went over. You should be familiar with what all these buzzwords are: MHC, these B cells, T cells, and whatnot. So if you guys don't have time, I went 4 minutes over. If you guys don't have time, you're free to go. But we do have a passage with about, I think, 6 questions here. So in the book, it talked about unideterminate, multi-determinant, multivalent. Do you think you can explain those? I would say don't bother with that jargon. Don't confuse yourself. Just stick with what's here. Just stick with what's here and don't bog yourself down with that jargon. You won't come into that for the MCAT. Alrighty, so let's see. We have 29, so a few people left, but I think we have a passage here that we'll go through that I think is very, very useful. I like it a lot, actually. It's more of a hormonal passage than the immune system. But let's go through it. I'll give you a couple minutes to read this and answer the first one. And then once you have an answer, send it in the chat and we'll go over it together. All right, so let's go through this. Alrighty, in terms of office hours, there is a question. Do dedicated to cell bio. I don't know how much justice I can do to cell bio or to, genetics in general, but I will discuss them at the end. So we'll get back to that. I'm not ignoring you, I promise. Okay. So there's also a question about highlighting. So typically for these questions, I look at this, and if I read the first sentence, there's a lot of jargon. Jargon sucks. So I try to ignore that as much as possible. So for a lot of bio, what I do is I just go straight to the question. But let's say I'm trying to actually go through this. Once you take a lot of practice exams, you can kind of get a sense of what the important topics are. So I'm reading through this in terms of highlighting. When I look at this, calcitonin is a polypeptide hormone. So I'm going to highlight polypeptide hormone, right? So why? Because that can tell you a lot of things, right? With solubility and whatnot. And so you'll see where I can use this later on. So polypeptide, where's calcitonin going to signal? Cell surface. Okay, secreted by parafollicular cells in the thyroid gland. Cool. 32 amino acids make up the hormone. Also, that's not bothering me too much. A disulfide bridge links residues 1 and 7. The entire molecule plus the disulfide bridge are required for biological activity. So I'm actually going to highlight that as well. That might come in handy. I'm not sure. CT works as an antagonist of parathyroid hormone. Okay. So I know what parathyroid hormone is, right? It gets released in times of low blood calcium. So right there off the bat, CT, calcitonin, and it works in times of high blood calcium. It's the opposite. In response to small increase of plasma release on the active kidneys to decrease calcium level. So I just inferred that from what I just highlighted. In the bone matrix, osteoblasts synthesize bone. We know that. They build bone. Osteoclasts catabolize it. They cleave it. We determined that earlier. Cool. The main effects of CT are inhibition of osteoclasts. So it's going to prevent osteoclasts from doing their things and a transient increase in urinary calcium. So it's going to mean is calcitonin is going to stop osteoclasts from taking calcium from the bones, and it's going to increase how much calcium you pee out. Also cool. Calcitonin is used pharmacologically as a treatment for osteoporosis. So it's used you have low bone density, low bone quality. Salmon CT is commonly used. Okay, although it differs markedly from human CT, it's about 30 times more potent. That's interesting. So it differs markedly. So it's different structurally. It's about 30 times more potent. I'm not really going to highlight that, but I'm going to keep that in mind. Treatment with CT is not without its own side effects. Okay, CT treatment for osteoporosis increases plasma PTH. And requires simultaneous calcium supplementation to avoid hyperparathyroidism. Okay, so I'm not going to worry about that too much. That's just a lot of jargon. So osteoporosis is a disorder of bone characterized by a decrease in bone quantity. So it just tells you what osteoporosis is. Most common in women following menopause and in elderly men and women. I don't really care about that right now. Which of the following conditions would lead to the greatest decrease in bone density? So it's like, oh, okay. So decreased osteoblast activity. Okay, so what would lead to the greatest decrease in bone quantity? So osteoblasts, they build it. So if we want to decrease bone quantity, we're going to want to decrease osteoblast activity. We're going to want to stop the building of that calcium. We're going to stop the deposit of that calcium on that bone. So I know right off the bat, A, that first part of A is good. B, we'll cross off B. I'm going to cross off D. Increase osteoblast activity will build more bone, and it would increase bone activity. So I'm right off the bat between A and C. And then decreased osteoclast activity. So decrease both activity, you're not really going to cause that much of a change. For C, decreased osteoblast activity, so you're not building more bone, and increased osteoclast activity, we're having more cleaving of the bone. So the greatest decrease in bone quantity, more cleaving, less building, I would go with C. Is there a cross-out function on the MCAT user interface? Yes, there is. You can strike through. It's called strike through. So I use strike through. I also do it mentally. So I didn't use strike through too much, but I think, yeah, it's called. There's highlight, there's tools on the top right corner of highlighting and strike through. So you can actually physically highlight and strike through. Okay, next question. What is the most abundant mineral in the human body? Okay, I'm not trying to stress you out who are still focusing on this question. This is one that you would want to build back up some time, save some time on. So what's the most abundant mineral in the body? So if right off the bat, just using, typical life skills, you always hear things like, oh, necessarily vitamins and minerals. B12, that's a vitamin, not a mineral, right? Vitamin B12. If you have low vitamin B12, this is just something, it can lead to anemia. So usually when people have anemia, you got to take vitamin B12 supplements. That's a vitamin, not a mineral. I'm going to cross out A. Water is water, not a vitamin nor a mineral. I'm going to cross out B as well. So now we have zinc and calcium. So when do we really talk about zinc so much? We don't really talk about zinc too terribly much, but calcium is used as a secondary messenger. Calcium is used for muscles. It's used for bone, and it is used at the terminal boutons because it binds to those vesicles and releases those neurotransmitters. So calcium is something that is very physiologically relevant. So right off the bat, I'm just going to look at it and be like, okay, we talk about calcium way more. Both vitamins, so both calcium and zinc are technically minerals. Most abundant, what it has is the most relevant here, calcium. Let me try to see. Awesome. Based on the passage, what is the role of PTH? So even if you forgot what PTH does, based on the passage, what is the role of it? All right, off the bat, just lecture what you need to know off the top of off the top of your head. PTH gets released in times of low plasma calcium, low blood calcium, takes it from the bones, brings it back in, right? So we should know that PTH increases plasma calcium. But how do you determine it from the passage as well, just in case you forgot, just in case you're stressed and you forgot that piece of information. So it says CT works as an antagonist of PTH. And so it does the opposite of what PTH does. And then the next sentence, it tells you what calcitonin does. So calcitonin works to decrease calcium level. So PTH is the opposite, must work to increase plasma calcium level. That's why it is A. Which of the following choices is a probable explanation of why salmon CT is 30 times more active in humans than human CT? All right, so let me kind of reword this question. In disguise, this is basically the very beginning of an endocrine lecture. What are the three things that can affect cellular response? Amount of the messenger, the number of receptors, and the affinity. It is that question. It's that in disguise. So one, if salmon CT is more resistant to degradation, there's going to be a higher concentration of messenger. It's going to sit there longer. Two, salmon CT attaches more strongly to the DNA of osteoclasts. What the heck is that, right? That one's kind of strange. Three, salmon CT attaches more tightly. So that means the affinity is going to be higher. It's essentially that question. It's that in disguise. And so that if that's the case, that's 1 in 3. Greater concentration of messenger, greater affinity. And so both those can create a stronger response. Just 3 more questions. If a person begins a calcium supplement regimen and doubles the calcium intake, what would be the immediate response in CT secretion? All right, so these questions are also a little bit more hard. These are really easy ones to overthink. And so if we just double calcium intake, what's going to be the response? So if we have a lot of calcium all of a sudden, what's going to be the response? Well, the calcitonin in the CT decreases calcium level. So if you have this really sharp, rapid response in calcium, the body is going to secrete more calcitonin to immediately compensate that response. 2 more questions. How is salmon CT calcitonin a polypeptide administered? This is a strange question, but you can do it. okay, this is a very strange question. How do you even answer this, right? You have all the information that you need though. So salmon CT, so how's it going to be administered? Is it going to be a pill for ingestion or is it going to be an injection? Right. And so it's a polypeptide. So that's our key here. Calcitonin is thus a peptide hormone. So ingestion to avoid allergic reaction. So, I mean, if you're bringing in something, it's a non-self. I mean, you can pretty much, if it's non-self, you're going to cause your body's going to recognize it either way. So ingestion versus injection versus allergic reaction. It's not really going to do much. It's going to do much different. If you're bringing it in, it is a non-self, and you will cause an allergic reaction if your body overreacts to it. So where you're looking now is ingestion versus injection to hydrolysis. So what the heck? Like, what does that even mean? So it is a polypeptide hormone. What gets digested in the stomach? Proteins. We have a protease in the stomach. We have that pepsinogen, right? That gets released in the stomach. We're going to digest the proteins in the stomach. So if we ingest it, it's going to get to the stomach and we will degrade it. So we don't want that to happen. So to administer it, we're going to instead inject it into the muscle to get into the bloodstream so that it doesn't reach the stomach. And not reaching the stomach will prevent it from undergoing hydrolysis, which is the method at which we break down proteins. So that is a really abstract question, right? It's making these connections where it's like, huh? But if you kind of think about it, right, it's kind of given in the question. It's a polypeptide. So that's why I highlighted a polypeptide that can tell you, where it's soluble, but also how the methods of ingestion, right? So we can actually take steroid pills, right? If we take prednisone, which is a pill, that can get it, we take that via pill, that's going to get into the stomach. That's a steroid. It's not going to be a peptide. So it's not going to be degraded. And so the fact that it's a peptide, if it gets into the stomach, we do have those proteases that will go in and destroy those bonds. The difficulty there, so what does he say the difficulty level of this question of the MCAT? I would say that maybe, oh gosh, I would say this is moderate to difficult in that because it's quite an easy concept, but kind of making those connections and recognizing what hydrolysis is makes it harder. And so a lot of people would like to choose this one as well, because it's just like, oh, for EpiPens, we inject blah, blah, blah. That's anti-allergic. So that's a very distracting one. And so how do you recommend studying material like this? Definitely more practice. Go through these questions, expose yourself to them, and see, did I get this one right or did I get this one wrong? So if I got it wrong, it's like, okay, so let's go back and reevaluate how I approach these. What is this actually saying? Where are the clues that pop up? So definitely more practice and recognizing these patterns is where I was able to figure out how to approach questions like this. So it is injection to avoid hydrolysis, which is just breakdown in the stomach, those proteases. And then last question, what are the symptoms of an allergic reaction to a foreign protein in the bloodstream? Alrighty. These are one of those that when you approach it, this is one that using, real life experience also helps. So allergic reaction. So we know that off the bat, we're going to have flushing and reddening of the skin, which is cytokines, right? So we know that one for sure will be correct. And so we look at right off the bat, well, A, B, and C all have one. Well, that doesn't do much help. Okay, so we just cross off C. 2, urticaria, hives, right? Okay, so when you have an allergic reaction to something, just in life, have you ever had hives, right? Likely, yeah. At some point, everybody's had hives. So just from personal experience, you realize, hey, that's also an allergic reaction. And then if you ever have people with anaphylaxis, all the inflammation in the body is going to cause inflammation of the airways, and it's going to cause bronchoconstriction and vasodilation. So you're going to have that flushing, but you're also going to have a difficulty breathing because you have all that inflammation. Your airways close off. So if you ever think of people who have bee stings through the EpiPens, people have or eat peanuts where you have the anaphylactic reaction, that difficulty breathing, that's just using that real-world experience to kind of confirm your suspicions. All these are caused by cytokines, however. So all 3 are allergic reactions. And where it says by a foreign protein in the bloodstream, that's going to cause an allergic reaction pretty systemically if it's in the bloodstream. So that is a distractor. So definitely will throw you off. But then again, try not to complicate it. If it's in the bloodstream, you're going to cause this reaction all throughout because the blood goes everywhere. So yeah, it's not going to be just in one location. It will be in the bloodstream. It will go throughout. And we do use cytokines to get that blood flowing and going throughout. So it's 1, 2, and 3. So for those of you who have stayed, I am sorry for going over. That was a lot of information. This is most likely my last ever TBR lecture. So thank you guys so much. It has been a pleasure. I will still be here though. So if you guys ever have any questions about taking the MCAT or just applying in general, always feel free to send me an email. I would love to help out. So even though this is my last one, I will still be here. You guys have my email. In terms of, I still do office hours, obviously. In terms of this week, office hours are kind of funky just because other work, but I would possibly be able to do a cell bio / possible genetics review in a couple weeks time. So I'll have an email sent out where you guys can basically do like an interest form and submit questions and whatnot. So that's something I'm willing to do, and we can have that happen in a couple weeks time. So definitely have Todd or someone send out an email for that. So thank you guys so much. Have great rest of your week. And if you're studying, if you don't show up to any office hours, wish you guys the best of luck. And it was a pleasure. Ooh, pre-lectures for some of the TBR. That's kind of tough with my set schedule. That might be a little bit more rough. Pre-lectures might not be an option, but I would be down to do office hours. I could do a lot larger sessions if needed. So thank you guys.